Hello friends, welcome back. If you are enjoying the content, don't forget to hit that subscribe button below. It really helps us out and you won't miss any future videos. Today we are solving random pick with weight. This is an interesting probability-based problem. Let's get into it. We are given a zero-indexed array of positive integers w, where w of I describes the weight of the ith index. We need to implement the function pickIndex, which randomly picks an index in the range 0 to weight of length minus 1 and returns it. The constraint to picking the index is the probability of picking an index I is equal to weight of the index I divided by sum of all the weights. Let's look at this example to understand the problem. We are given with w equal to this, and the function pickIndex has to pick one of the indices 0, 1, or 2. And probability of picking index 0 is equal to 1 by 10, where 1 is the value at index 0 and 10 is the sum of all the values in w. Similarly, probability of picking index 1 is 3 by 10 and probability of picking index 2 is 6 by 10. If we imagine w as a list of candies, then we have 3 candies right now. Candy 0 has weight of 1, candy 1 has weight of 3, candy 2 has weight of 6. Let's say we have all these 3 candies in a container like this one. And the role of function pickIndex is to reach into this container and pick one of the candies. Probability of picking candy 2 is higher because its weight is 6 out of 10. And similarly, probability of picking candy 0 is lower because its weight is 1 out of 10. To solve this problem, we can break these candies into pieces of weight 1, and on each run of function pickIndex, we have to pick a piece of candy of weight 1 and return its index. So this is what the list looks like if we break these candies into pieces of weight 1. So there are 10 pieces of candies here, where each piece is of weight 1. There's only one piece of candy 0 because candy 0 has weight 1. And there are 3 pieces of candy 1 because candy 1's weight is 3. And there are 6 pieces of candy 2 because its weight is 6. And we divided it into 6 pieces, each of weight 1. So now what pickIndex function has to do is randomly pick one of these indices and return its value. This satisfies the given constraint because probability of picking a piece of candy 0 is 1 out of 10. Probability of picking piece of candy 1 is 3 out of 10. And probability of picking piece of candy 2 is 6 out of 10. The runtime complexity of this approach is big O of t is the total number of pieces of candies and n is the number of candies. Do we really have to build this new array to solve this problem? To find out, it makes it easier if we change this array from 0 indexed to 1 indexed, like this, where 10 is the sum of the original input array w. So we have to randomly pick an index between 1 to 10 and return its corresponding value in this array. So the question is, can we find this index's corresponding value without having to build this array? The answer is yes. For that, we have to look at the ranges of these indices. For candy 0, the indices range from 1 to 1 because there is only one piece of candy 0. For candy 1, the indices range from 2 to 4. And for candy 2, the indices range from 5 to 10. When we pick an index randomly from 1 to 10, we need a way of mapping that index to one of these ranges without having to build this new array. This mapping can be easily derived from the drawing over here. We thought of this as a container, and these 3 circles are candies of different weight. So the candy 0 goes from 0 to 1 on the x-axis, candy 1 goes from 1 to 4 on the x-axis, and candy 2 goes from 4 to 10 on the x-axis. So if we look at the end of these ranges, 1, 4, and 10, they match with the end of ranges over here, 1, 4, and 10. Why do they match? They match because we are breaking these candies up into pieces of weight 1, and each cell in this array is a piece of candy of weight 1, and each unit in this x-axis is a piece of candy of weight 1. That's why they match. For the same exact reason, if we took the prefix sum of this input array w, which is 1, 4, and 10, and this prefix sum matches with the end ranges of each candy we saw before, which is 1, 4, 10. So basically, we have to pick a random number between the range 1 to 10. Let's call this x. And we have to find the first index in the prefix sum array whose value is greater than x. Let's say we pick the integer 6, which is equal to x, and we scan through this prefix sum array and find the first index whose value is greater than 6, which is 2. So we return 2. Next, let's say we pick 2, which is equal to x, and we find the first index whose value is greater than 2, which is 1. So we return 1. So once you understand this mapping, it's easy to see that this linear search operation is doing the exact same thing we did using this new array we had built. So that means we don't have to build this new array, we just have to find this mapping. And the mapping is basically finding the prefix sum array, which brings down the runtime complexity to O of n. But we can further reduce this complexity to O of log n. Because the values in this prefix sum array are sorted in increasing order, that means to find the first index whose value is greater than x, we can apply binary search. So that's our final algorithm. Let's apply this algorithm on a different example. Here is another example, w. Sum of all the elements in w is 15. I've already written down the prefix sum array for w, where the first element is the same, and the second element is first element plus 4, 1 plus 4 is 5, 5 plus 3 is 8, 8 plus 2 is 10, so on and so forth. So now we start by picking a random number between 1 to 15, where 15 is the sum of w, and we call it x. Let's say the random number we picked is 7. So we have to find the first index in the prefix sum array whose value is greater than 7, and we apply binary search for this. In binary search, we have two pointers, left and right. Next, we find the mid element, which is L plus R by 2, which is equal to 0 plus 5 by 2. We always round down, which is 2. So we check if the value of index 2 is greater than or equal to 7, which is true in this case. 8 is greater than or equal to 7, which means every index after the index pointed to by m will have value greater than 7, which implies we can get rid of the right half. So we move the right pointer to m, and we continue doing binary search. Now m will be 1 plus 2 by 2, which is 3 by 2. We always round it down, which is 1. Next, we compare the value pointed to by index 1, which is 5, to x equal to 7. 5 is less than 7. That means any index below this index pointed to by m will have values less than 7. So we can get rid of the left half. So we move L to m plus 1. Now both the pointers point to the same index. That means we have found the first index whose value is greater than or equal to x, in this case 7. So that's our algorithm. As we discussed before, the runtime of this algorithm is big O of n, where n is the number of elements in the given input array w. So let's write the code for this algorithm. First, we start by building the prefix sum array. Let's call it prefix. But basically we need to maintain a running sum of weights starting from 0 for weight in W, add it to W sum, and append that to the prefix sum. But append W sum. We also need the sum of all the weights. Let's call this total, which is equal to W sum. Next, in the function pick index, we start by picking a random number between 1 and total using the Python library random. Random dot randint between 1 and total. We called it x. Next, we need to do the binary search to find the first index in the prefix sum array whose value is greater than or equal to x. We have two pointers, L and R. L points to the first element and R points to the last element of the prefix sum array. While L is less than R, we find the mid index, which is L plus R minus L by 2. We check if the value of the mid index in the prefix sum array itself, the prefix of m, is greater than or equal to x. That means all the values after this is also greater than or equal to x, and we can get rid of the right half by setting r equal to m. Else, we can get rid of the left half by setting m plus 1. When both L and R pointers point to the same element, we return that index. Let's try to run the code. As you can tell, the submission goes through. If you found this video to be helpful, please support by liking the video and subscribing to the channel. I will see you in the next video. Thank you.